Alright, so in this lecture we're going to take a look at variable amplitude loading and plasticity and talk about something called material memory. Now we've kind of alluded to this a little bit, although we haven't explicitly shown this yet. In the past couple of lectures we've talked about cyclic loading and unloading and creating hysteresis loops, the Massing's hypothesis, the Bauschinger effect for cyclic loading. Now we're going to take a look at more general variable amplitude loading. This will be important to us for a couple of reasons. One is it's going to allow us to calculate stresses and strains under variable amplitude loading, but the other is it will help us in identification of cycles, hysteresis loops. These hysteresis loops will be the smallest bit of item that we will calculate fatigue damage for. So toward the end of the semester we'll talk more about rainflow cycle counting, but I want to introduce the idea of identifying hysteresis loops now so that makes more sense at that point in the semester. Okay, so let's talk a little bit about what we mean by material memory. And for this, I'm going to motivate this by some stress time histories. It's a little easier for me to draw these plots as if I think they're stress controlled, but you can do strain controlled plots in a very similar kind of way. So this will be the stress versus time history, and maybe just to illustrate this, we'll load it up to some point, we'll unload it, and we will reload it back. So I'm going to label this, I'll call this one O for the origin, and then A, B, and C. Now when I make these sketches, the sketches are going to be just that, just kind of illustrative sketches of what goes on in the hysteresis response. In order for these to look reasonable, I'm going to assume that we have a little bit of plasticity involved in these hysteresis loops. It's not necessarily the case in the actual material behavior unless you have significant amount of plasticity. So just keep in mind that I'm exaggerating the plasticity effects for the most part. And I'll try to point that out as we see some of these examples. Okay, so here's an example, and let's talk about what happens in the material response. And now I'm going to plot stress versus strain. So my material starts off, it's either untested or maybe it's a cyclically stable material. We're not going to worry about transient effects. So it starts off at, say, 0 stress and strain, and we load it up to point A. Now if this was purely elastic, it would be along this path, but I'm going to, like I said, assume that there's a little bit of plasticity, so maybe it does something like that, and that location is point A. I'm going to unload it to point B. Now I can unload it all the way down to 0 stress if we want, or we can go into compression if we want. The ideas are all very similar. It depends on how much plasticity we have and whether our stress goes positive or negative. But let's say we just unloaded a little bit, and in that case what we talked about is the unloading slope initially would be basically the modulus of elasticity. Now if we use the Ramberg-Osgood description of the material behavior, remember the Ramberg-Osgood equation always has a little bit of plastic strain in it. Even though it might be a tiny number compared to the elastic strain, there always will be a small width of the hysteresis loop using the Ramberg-Osgood equation. When you do the calculations, you'll see how small that can be, and in some cases it's so small as to be negligible. So just keep in mind it initially unloads at the slope E, but we might have a little bit of plasticity. So we go down to point B. Okay, so now we've taken, let me use a different color here, we've gone up to A, we've come down here to B, and we have to pay attention to what happens when we reload it from point B all the way up to point C. Okay, we initially load it, and we close this hysteresis branch, which closes that hysteresis loop, ABA. Now here's the interesting thing about metals. materials in general, is that once that loading has reached the previous highest level, it continues on as if that excursion from A to B to A had never even happened. It ignores that excursion. Now, does it completely ignore it? Well, not necessarily, but this is a really good model for what happens in a lot of metals in particular. Okay, so when it goes from O to A, comes down to B, it reloads back up to A, and then it continues on from A to C as if this ABA had never even happened. So if we were to go to the lab and test this, we would see that. We would see if we loaded it from A all the way up to C, it would take this, from O all the way up to C, it would take this path, just like this. But if we went from O to A to B to C, it would follow the path after this excursion happened, as if the excursion from ABA had never even occurred. Now, there are physical mechanisms for this, and there's some explanations. You know, depending on how you want to think of this, if you have a metal that has all these grains in it, there's lots of grain boundaries. If you have a small level of unloading, then that small level of unloading does not affect the overall breaking through of dislocations and grain boundaries. But when we go from A to C, all of that little stuff that happened from A to B to A doesn't really matter anymore, because now you're moving these things around from A to C in a much higher level of load. It's breaking things up easier. It's making those systems glide faster or easier. Not necessarily faster, but easier. And so it's kind of like that little thing from A to B to A was so inconsequential that it didn't matter from A to C. Now, even in larger levels where B goes further down or goes back to zero, that's still the case. Okay, so the material has what we call this memory. It has the memory of where it left its stress strain curve. There is also a multi-axial analogy to this that we'll touch on toward the end of the semester. All right, so this is kind of the key to understanding what goes on in the material. Now, we have equations. We've talked about the hysteresis branch equation. We've talked about the hysteresis loops. We've talked about the monotonic stress strain curve. So we actually have ways right now to calculate all of these things if we're careful. And I might make a separate video, or I might do some calculation at the end of this one to kind of see to practice using those equations that we have. But for now, the important thing that I want you to get out of it is to understand what happens, to be able to try a couple of these on your own, and most importantly for us is to be able to identify hysteresis loops, which will be the damaging event that we have for fatigue loading. If we can identify hysteresis loops, then we have it everything we need with the material properties to calculate fatigue damage under variable amplitude loading. All right, let me save this page. Let's just do a few examples. All right, so here's another one. I would suggest you take a look at this, and based on what we talked about, pause the video and see if you can sketch what happens to the material behavior that we have. All right, so I'm going to sketch here the stress strain response, and here's my point O. I'm going to go up. I have maybe a little bit of plasticity. Here's my A. So the first part starts out just like previously. We go down to B. When we get back up to the stress level of A, it rejoins the stress strain curve as if that never happened. We get to C, down to D, back up to C. We get to E, F, and G. So what hysteresis loops do I have? I'm talking about the stress ranges. We have an ABA. We have a CDC. We have an EFE. And then if I went into the lab and just tested the material from A to G, it would follow that same path that I just drew in red, as if those little excursions hadn't ever happened. Now if I wanted to calculate O to G, okay, I would use our Ramberg-Osgood description. So I would say that epsilon is equal to sigma over E plus sigma over either K or K prime. I'm going to call it K prime if we have a cyclically stable material. Sigma over K prime to the 1 over N prime power. And that would describe every part along the path O to G continuously. If I wanted to describe the hysteresis branch ABA, I would use the hysteresis branch equation. Let me do that in blue. Delta epsilon over 2 be equal to delta sigma over 2 divided by E plus delta sigma over 2 divided by K prime, so 1 over N prime. Now here we have to be a little bit careful about what we use for our values for delta sigma. For the loop ABA, we would use AB for my delta sigma. Okay. So let's put some numbers on here. Maybe this was 100 megapascals and this was 90 megapascals. Okay, so in that case my delta sigma would be equal to 10 megapascals. And then of course I divide it by 2, divided by E, divided by 2, divided by K prime to 1 over N prime power. Multiply the right hand side by 2, and then I get my delta epsilon, which will tell me how far over to the left I would go during my unloading, and then it would tell me how far over I would go, which should mate back up for my other branch from B to A to join that curve. Now here's a thing to keep in mind. If you were to do this, you would have to remember that first you used the monotonic equation from O to A, the branch equation from A to B, using this point as your origin now. So the delta epsilons start from here, and then once you close this hysteresis loop, the portion from A to C would go back to this line, but using this origin and starting from A to C to complete that section of the branch. So again, we'll have an example of some numbers that I think will make this clear. But again, focus for now on the shapes and the branches. Let's do a few more examples. All right, let's look at this path. So here we have from O to A a big tensile stress. We go down and reverse it down into the compression side at B, and then we cycle it back and forth. And my intention here was to show that C, E, and G all have the same levels of stress, B, D, F, H also have all the same levels of stress. So let's see what this might look like. Okay, start off my material. I get to point A. I get down here to point B. Again, maybe I've exaggerated the plasticity, but you get the idea. And then here we have to C. To D. Back up to E. Back down to F. Back up to G. And then back down to H. All right. So this is a way to set up a very large compressive mean stress on that hysteresis loop. What loops do we have? Well, we don't have any loop that involves A because it's just a branch. It's a monotonic, then a branch from A to B. But then we have all these loops that are going on here. Let's see what we have. First of all, we went C down to D. So we went B, C, D. We went D, E, H. Excuse me, D, E, F. And then we have an F, G, H. Okay, so those would be our hysteresis loops that we have for that one. You'll have a homework problem, I think, that will set this up. All right, let's try another one. All right, so here's a stress time history. Let's plot the hysteresis response. Here we are at O. We go up to A. We go down to B. We go back up to C. Now when I draw this, notice I'm trying to draw this as if A to B, and this portion from B to C, it's symmetric. It's going to form a hysteresis loop when we go all the way up to A. So I'm trying to make it so that it's kind of symmetric looking. Sometimes it's hard to do, but do the best you can. All right, so we went from B to C, and now we're going to go down from C to D. And people complain when I don't bring this into compression if this is compression. So let me extend this all the way down to here. And now, when I go from C all the way back up to A, or the point E, same level as A, what I do then is I'll try to maybe dash this in red, is first I close off this hysteresis branch, CDC. Okay. Now I forget that this excursion happened, and now I rejoin this branch from B to C to A. So in this case I have two closed hysteresis loops. Now each hysteresis branch has a different origin associated with it. Each hysteresis branch has a different stress range associated with it. And when I close off the CDC hysteresis loop, then I have to go and use this as the origin and calculate from C to A to get that hysteresis branch. Okay? So even though when we use our material properties, the K prime and the N prime would be the same, and we even use the same equation, we have to be really careful in how we apply it, because the delta sigmas for this branch from B to A always use this as the origin, and the delta sigmas from C to D back up to C use either this point or this point as their origin. And the stress range is a lot smaller from C to D to C than it is from A, B, E. Think about that for a little bit. It'll make the most sense if you think about it on your own. We will get into calculating these things and so forth, but do think about how that all works out. Let's try one more. All right, let's make this a little trickier. We started our origin, we go up to the high point A, down to B, C, D, E, F, and G. It's the same level as A. We're going to see if we can identify the hysteresis loops in this short little time history that we have. And I'll do the best job I can. At this point, I can say I might have to redo this, but I'm not going to stop the video this time. I didn't like the looks of my hysteresis loops last time, so I actually stopped. But if I mess it up, we'll just try it again. It can be a little bit tricky to sketch these out. All right, so I start off stabilized material, point O, origin right here. And then I go up and I use my branch equation. And I have some plasticity, so I get to point A. Now, at the beginning of the semester, we started off with our project where I said, I want you to rearrange a time history so it starts and ends with the same largest peak. The reason why we do that is if we look at this hysteresis response, we're only going to be using the initial Ramberg-Osgood equation for the beginning of our setup of our hysteresis loop calculations. Everything else will be based on the hysteresis branch equation. Again, that might make more sense a little bit later. So we're here at point A, and now we're going to have some unloading, and we're all the way down here at B. Okay, we go this way, and we have some tension, and we're at point C. Now, is the strain positive or negative? I don't know. I just know that in the end I want to have a nice looking picture, because it's not about calculating the values right now. It's about identifying the hysteresis loops that we see. Okay, so that's point C. And then I come down to point D. I go over to point E. And again, I'm exaggerating the width of these things. Come down to F. Okay, now look at all, we don't have any closed hysteresis loops yet. None of our hysteresis loops are closed. We've used the hysteresis branch equation if we want to calculate these values many times. So let's see, 1, 2, 3, 4, 5 times, but we haven't closed any hysteresis loops yet. Now let's take a look and see what happens when we go from F all the way back up to A. And okay, F should actually be negative also, so we can do that. Like I said, some people get real concerned when I don't show them in the right quadrant, but for purposes of loop identification, it doesn't really matter. Okay, let me switch over to red. Now, when we go from F all the way to A, we start going up here, and when we hit to this value that corresponds to here, that's that point right here. Now we've closed off a hysteresis branch, E, F, E. when we do that, it's kind of like this excursion from here to here to here doesn't even exist anymore. Okay, what would that time history look like? Okay, so this is where F used to be, but it goes from D all the way up to E, all the way back up to G or A. So now it's just like that. This excursion wasn't even around. Now at this point, it rejoins the hysteresis branch that started at C, went down to D, and now we're going to get up to the level of C. So we have a C, D, C hysteresis branch, hysteresis loop. Okay. So it went from here to here with the branch equation. Now we're going from here all the way back up to C with the branch equation. We forget about this hysteresis loop EFE. We reset, this is the origin, and we go from here to here. Okay, so now it's like this C, D, back up to here doesn't exist. So this is gone. And now what we have is an A, B, A cycle. We did the A and the B. We did the B all the way up to point C. Now we do the rest of it. Which would be that part of the hysteresis branch. And now we have a closed loop A, B, G if you want, or A, B, A. So we end up with 3 hysteresis loops in our stress-strain response. This hysteresis branch from A to B is straightforward. The hysteresis branch from B to A, well, first we did from B to C, and now we're using this as the origin, and we're doing from C back up to A. Forgetting that these other 2 even happened at all because of that material memory. Alright, I think I'm going to stop this video here, and I'm going to do a part B where we use some numbers to calculate some of these things.